Welcome. In this session on natural deduction, we'll go through some definitions. The first definitions that we'll have is a model. And a model, which we'll write as a script M, is an assignment of true or false to every propositional atom. And a reminder is the propositional atom is, these will be P, Q, R, etc. And we will overload, which is to say we'll have multiple definitions, overload the symbol for semantic entailment. And what we'll do is we'll say that a model entails a formula is defined as C evaluates to T under that model. So an example would be that if this formula was a conjunction of P and Q, that this entailment would hold if and only if both P and Q were T in this model. And we'll also say that gamma is a set of formulas, and we'll use the symbol phi here because we're meaning mainly that these are going to be premises in a logical argument, but for us they're just formula. And we'll say that a set of formulas entails another formula is defined as, and now we'll go to that semantic entailment definition that we had in a previous session, is defined as for all models such that every formula in the set of premises evaluates to T the formula C evaluates to T. And note that we're using that this and this are different senses, they're different meanings of this entailment. And this one matters a great deal in advanced courses. We'll deal primarily with this one. So having those basic definitions, we can now go to some definitions that employ them. One is a tautology. So a tautology is a formula that is always true. C is, and let's put that in quotes, always true. And what we mean by that is that we say that for all models, M semantically entails the formula. And we will write this as, because this is true for all models, what we'll usually do is we'll say that C is a tautology, and we'll write that as C is semantically entailed by anything at all. So that's a tautology. The next term that we want is a satisfaction. So satisfaction is, we will say that C is satisfiable. So that's the term that we're going to define. Is satisfiable is defined as there exists a model M such that M semantically entails the formula. And as we compare these, we can see that satisfaction is a strict subset of tautology. That is, a formula can be satisfiable and not be a tautology. A formula can be a tautology and therefore it's always satisfiable. Satisfiability is a really important concept in advanced logics, and it's one that we can explore here in propositional natural deduction. And when we get to a further form of natural deduction, we'll find that this notion of satisfiability becomes quite complicated to determine. A final term that we'll define here is semantic equivalence. And this means this is written as phi is equivalent to C. And we use this mathematical equivalent term. What we mean is this formula is semantically equivalent to that formula is defined as the first formula semantically entails the second, and the second formula semantically entails the first. I'll now erase this and we'll go through one very brief example of semantic equivalence. Let's consider two formulas in propositional logic, and we'll use a truth table to demonstrate their semantic equivalence. These formulas will have 3 atoms, and so the truth table will have 8 rows. Let's suppose that we have this, that P conjoined with Q implies R, and let's have P implies Q implies R. And what we want to do is determine whether or not these are semantically equivalent. Here we can immediately fill in parts of these. Whenever this consequent is true, it is implied by anything. So we can immediately fill in half of the truth table. We then know that this entire implication is true if this is false and this is false. So here we know that where this is false, the conjunction of P and Q is false. Here we have the conjunction of P and Q is false. Here we have the conjunction of P and Q is false. This is the remaining row, 1, 2, 3, 4, 5, 6, 7. And this is, if both P and Q are true, the antecedent evaluates to T, the consequent evaluates to F. So this is false. We can now likewise go through this and we can fill in its truth table. We know that a false antecedent implies anything, And that means that we can immediately fill in these last 4 rows of the truth table. So that will be T, 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 T. We can now consider those situations in which the antecedent is true, and now we have to look at the consequent. When we go into these, when does Q imply R? Well, if Q is true and R is true, then this is T, and the entire implication evaluates to T. If Q is T and R is F, then this is false, and T implies F does not hold, so that is false. If Q is false, then it implies anything, and so this antecedent, this consequent, evaluates to T, and so T implies T, and that's the case. When we work this out, what we've done is we've shown that this formula and this formula are semantically equivalent. So what we've shown is, we've shown that P conjoined with Q implies R is semantically equivalent to P implies Q implies R. This semantic equivalence, we can see here, means that this formula semantically entails this formula, and this formula semantically entails this formula. Because natural deduction on the propositional level is consistent, complete, and correct, for every semantic entailment, there is a corresponding proof of a sequent. We haven't proved that this, from this premise, we can arrive at this conclusion. But from this truth table, we know that there exists a proof where this is the premise and that is the conclusion. And we also know that there exists a proof where this is the premise and this is the conclusion. So we're able to use semantic entailment to tell us when formulas are semantically equivalent, and that semantic equivalence, as a result of our metalogic, tells us something very important about sequence.